Hello. Now that we're done with the electrical system, electrical networks, transfer functions of electrical networks, and also the translational and rotational mechanical system. Now we will be talking about the combination of the two. We call them the electromechanical system. So this is just the a system that composed of electrical system and also a mechanical system. And most examples the typical examples of electromechanical systems are the what we call the transducers. Transducers, these are devices that converts one form of energy into another form, usually electrical and mechanical energy. And there are two types of transducers. We have the actuators, and we have the sensors. Examples of actuators, these are motors. We also have relays and magnetic contactors, so on. So these are devices that if you apply a electrical energy, it will be converted into mechanical energy. While sensors is the other way around. It's if you apply mechanical energy, it will result to an electrical energy because they are sensors and they are used as sensors in control system. One very typical example, very basic example of a sensor is the potentiometer. 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 This is a sensor. It's commonly used as a sensor in control engineering, and it's an electromechanical system. Why? Because this is just a variable resistor with three terminals. The resistance here is varying by rotating. So if you rotate the potentiometer, you're doing a mechanical energy, and the output here will be an electrical energy. Because if I let a voltage here, plus or minus E into this circuit, then if I rotate the this variable resistor here, the voltage at this point will also vary. So if this is uh, E1 or E2, or we can just make this capital E here because this will be constant. The voltage source of this one will be constant. What we vary here is the rotation or the angular displacement here. So there's an angular displacement theta, and it will result to a certain voltage is of T. And this change depends on the position of the rotation of the potentiometer. And this is what they used in measuring the angular displacement. So they use potentiometer to do that. And if we derive the transfer function of this typical example, this is actually a zero order system. This is an example of a zero order system. We already discussed this, the different order of system. We have zero, first order, and second order system. Why is it zero order system? Because it's just a resistor. It's just a resistor. So what is our input? What is our output? Our input is the displacement. We rotate the potentiometer and it will result to a voltage drop across this terminal here, and they are just directly proportional. That voltage is actually just proportional to that angular displacement in time domain. And if we solve the transfer function, so this is this is of t. If you remove that proportionality symbol with equals, change it with equals, then we will introduce a constant, proportionality constant. And this constant is actually in terms of because E is voltage and theta is in radian, then the unit for this will be just volt per radian. volt per region and multiply it with theta t. If you take the Laplace and solve for the transfer function, this is just output over input. Theta is the input and our input is the voltage, or our input is this theta is our input. Our output is the voltage. So we can just write this into the S domain, theta S, or this is the input. The output is the voltage E of S all over the input theta in S domain, and this is just equal to a constant K. So this is a zero order system. So you don't have any S in the transfer function because this is a zero order system. It's S raised to 0. So that's the first example of a potentiometer. It's just a zero order system. Then we look at a DC motor for the actuator. Let's take a look at a permanent magnet DC motor. Let's try to model uh, this system. So when we say permanent magnet, the field is a fixed field. So we have a rotor. This is our rotor. So this is the conductors. Then this is connected to a shop here. Then around this is it's just a permanent magnet. Then if we apply, so from your DC machines, you already discussed this in DC machines. Then this shaft here is actually a bearing here. And we can model this into two parts, again, in electrical and mechanical parts. So this will rotate if we apply a certain voltage at the terminals. And if it's a brushless DC motor, so there will be no, so let's just make it brushless. So that there will be no voltage drop across the brushes. So we will divide this into two parts. First, let us look at the electrical part. Electrical system. So here, what do we have? We have a voltage source V. So it's a DC motor. So let's call this V of T. Then we have a wire here. And we know that wire has a resistance, and also in the armature, you can just call that R. The resistance of the wire, if you have another circuit here, then plus the resistance of the armature. Then because the rotor, the coil, this is a coil. So a coil means an inductor. So we have also an inductor, LA. We can just call it, if we make the resistance of the wire here at the input to be negligible, then we can just look at the resistance of the armature. Then there's a special thing about these DC motors. When they are rotating, apply voltage and they rotate, and this rotation will also cause it generates another voltage here, and we call that one the back EMF. If you remember this, let's just call it VB. So this is the back EMF, and that back EMF is proportional to the speed of the rotation of the shaft or the motor. So VB T is just proportional to the speed of the rotation. What's the speed? We have, you can just put here theta dot. So means it, where theta is the angular displacement, theta dot is the velocity, angular velocity. Then this is a complete circuit. So we can just apply our KVL here. So if we have the voltage source V of t, then minus the voltage drop across RA. So that is just we have a current here IA. We can just call it IA, armature current. And the voltage drop across RA will be IA times RA. Then we have the voltage drop across the inductor. We already discussed this. Inductors is a these are devices that stores energy. So what's the voltage drop across an inductor? It's just equal to L di, our current IA dt. And finally, the voltage across here, the back EMF VB of t. And this is equal to 0. And what is VB of t? From here, we can just say that VB of t, or the back EMF, if we remove that alpha here, we can just call this one the back EMF constant times theta dot t. And we can substitute it here. So we have B of t minus IARA minus L DIA dt minus that one KB theta dot t. And this is equal to 0. And you can apply the Laplace transform to convert this. These are all in t domain, so we need to convert them into s domain. So we need to apply Laplace. So this will be V sub s minus RA times I say IA sub s. And here this is a derivative, assuming no initial condition, just like always, this will be equal to s times L times I sub a. This is in s domain, then minus k b, and this is also, we convert this into the s domain. This is a first derivative. Again, this is a first derivative, so we need to multiply it with s. And no initial condition, so let's just make this one convert this one in s domain, and this is equal to 0. Then we call this our equation 1. This is our model for the electrical part of the DC motor. Then for the mechanical part, mechanical system, because this is a rotating mechanical system. This is a rotating device. So the concept that we will be using is the rotational system, rotational mechanical system. And there's a shaft. In the shaft of the motor, there's a bearing. So we can just model this into, we have a mass of inertia, the core, or the rotor. You can just call it JM if you want. Then somewhere here, there's a somewhere at the shaft, there is a bearing that can be modeled as a damper here. So this is the damping, and this is actually rotating. Then in other symbols, so J, this will be connected to a damper. Then we will be rotating this. This will be theta. This is our theta. In that theta, we also have torque, our torque. And now, so the free body diagram. So there's no spring, rotational spring here, because we will assume that the rotor is, there's no it's the strength of the material used here is good enough to resist the rotational spring. So we can just write the free body diagram. Theta is going into that direction. So we have also our torque in that direction. And what else? We have the resisting parts. We only have, let's call this one KD, or the damping constant of the damper. And it will be at the opposite direction, the torque due to damping. And we don't have torque due to spring. So from here, apply our concepts in rotational systems. Applying is the summation of all torques clockwise direction positive, and this should be equal to what? This will be equal to J times the second derivative, or the angular acceleration, or the second derivative of the displacement, angular displacement. And what are the torques here? We have positive T here, tau, and we have minus the tau, or the torque due to damping, and this is equal to J theta double dot. And what is our tau here? Is this tau here, our the tau due to damping? We already discussed this. This is just equal to what? The damping coefficient multiplied by the speed, or the angular velocity, and this should be equal to J double dot T. Then we can apply our Laplace. Or before that, we need to also solve for this tau here in terms of, so that we can connect them to the electrical system. The formula for the torque, if you remember, in DC machines, our torque is actually, this is proportional. In general, torque is just proportional to the armature current and also the flux of the field. But in our case, in our example here, our flux, because we use a permanent magnet to our field, so the flux on the field is constant. So we can just say that the torque is proportional to IA, or the current IA. This should be in small letter. IA. Or torque is just equal to another constant. This is due to torque. Let's just call it KT. The torque constant times IA. And we can substitute this here to our system, so that we can remove the tau, because we don't want the tau in our equation. Remember here, I forgot to tell you, our input should be, the input is the voltage V, and our output, you can set at our output to be the angular displacement theta. You can also use the angular speed or the angular acceleration if you want. You can just change the formula later on here. So I need to substitute this in this equation, so that the torque will be will disappear in the equation. So this will be KT times IA minus KD theta dot in time domain, and this is equal to J theta double dot T. Then I can now apply the Laplace transform. So this will be equal to KT capital IA minus KD. This is the first derivative, so I need to multiply it by S. Theta S minus, or equals J. This is the second derivative, so this will be S squared. And no initial condition, so theta S. Then this will be our equation 2. Then I can just copy our equation 1 here and put it here. And we can solve for the voltage V. We need to retain V and also theta. Other variables here should be removed, just like IA. So I can solve for IA in the equation 2 and substitute that in equation 1. So from equation 2, IA now, KT IA will be equal to J S squared theta S minus, or this will be plus, so plus K ds times theta S, and solve for IA. So IA now will be equal to, divide both sides by KT, this KT here, so this will be J divided by KT times S squared, and I will factor out the theta S, then plus KD all over this KT again, multiplied by S, then this whole term is multiplied by theta S. So this will be our IA, and we will substitute this into equation 2 or equation 1. And from equation 1, we can also factor out this IE here. So we have RA and SL. So this will be V sub S minus, we factor out that IA, this will be SL plus RA. Or did I call this one LA? This should be LA. To be consistent, let's just call it LA and RA. LA, then we have also here LA, meaning the armature inductance. That's fine. Then this will be S times LA. And we multiply this with IA because I factor out this IA. But IA is equal to this, so I just need to multiply it with this one. Let's copy this one, multiply it here. So this is our IA here. Then after that, we still have minus KBS theta S here. So minus KB times S times theta S. And this is equal to 0. Now, if we look at our equation, these are in terms of the voltage and only theta. The others, these are constant. LA, RA, J, KT, K, those are all constants. So we remove the other variables in our equation by just substituting the values here. Now, if you want to determine the transfer function, the output over the input, our output, remember, is theta S. Our input is the voltage. So we can put this two terms here at the right side. It will become positive. So V sub S now will be equal to this one, SLA plus RA multiplied by J over KT S squared plus KD over KT S. Then I will factor out again the theta S. So minus this one, KB times S. Then you multiply it with the theta. Then theta over V sub S. Output over the input V now will be equal to the inverse of this. So this will be 1 all over this whole thing here. Then we can still simplify this. We can make it into the general form. This is GS squared minus KBS by distributing the terms here, or we can also simplify this because in DC motor, the value for the inductance LA, if we is much lesser than compared to the RA in terms of millihenry up to microhenry. So this is a very small value. So if we try to substitute the value for that here, we can just disregard this LA here, and we can just look at RA times this to simplify also our transfer function. This is only true for DC motor, permanent magnet DC motor. But the general for transfer function for a motor should be equal to this one here. So if we remove LA, very negligible LA, so theta S over V sub S now will be equal to 1 all over, this will become, we can factor out KT again here. So we have RE over KT. Then we have S squared plus JS squared plus KDS minus, this minus KB times S. KB times S. Then simplify further. What can we do here? We can convert this into a general form so that we can determine our different parameters, the zeta, the omega n also. We can also determine the time constant if you want. So this will be, I can multiply this whole thing by RAKT. And also I need to remove this J here. So I need to multiply this with that inverse. This will be, to remove this J, we have KT all over RA. So this will cancel out. Then also I want to remove the J here. So I still need to divide it by J. So what I did in the denominator, I need to multiply it again at the numerator, RAJ. Then if we distribute now, this will be KT all over RA times J all over, this will be S squared, this will cancel out. Then plus, R, this will cancel out again. I have J here, so this will be KD over J. KD all over G times S. Then minus this one will be KB. Is this KB or KD? It's KB. Here, this is KD. This is KB times KT all over RA times J times S. Then we can just add this or subtract this. To simplify further, we can also factor out 1 over J here. And factor out S, we can also factor out S. So this will be the transfer function now will be equal to KT all over RA times J all over S, factor out S. Then I have S plus this 1 over J. Then you multiply it with 1 minus the KB times KT all over RA. And this will be our transfer function for a DC motor. Remember, this is for if you have a very negligible LA or an LA that is much lesser than the value for the armature resistance.